Okay, small introduction. My name is Roman. I'm an engineering project manager at SDC Verifier, and today's webinar is going to be about the post-processing, about the peak finder tool and the governing loads tool in SDC Verifier. So we are going to talk how to find out how to understand behavior of your structure under the loads of your complex structure, having a lot of different load situations, how to determine the cause of the high results to be able to solve the problem afterwards through the reinforcement or calculation improvement. I'm not sure if everybody of you is aware of the of our software about the main capabilities. So basically, I will spend 2 minutes and describe it briefly. So what is SDC Verifier in general? This is an engineering software to perform structural verification according to industry standards. So basically, this is a powerful post-processing tool which is made on top of the popular FEA programs like ANSYS, FEMAP, and SimCenter 3D. And on my screen now, you can see the standard workflow of the SDC Verifier. So the main idea is that if you build up your finite element model in one of those 3 software, you're able to apply multiple different load combinations having different factors with the help of SDC Verifier. And when the structure is analyzed, basically you accounted for all these kind of load situations. You need to perform checks according to different standards. But as you know, all these structural checks, they should be done on top of the structural items like beam members, welds, plate fields, and so on, and not finite elements. For this reason, we have the recognition tool in our software. This tool helps to automatically determine structural members out of the finite elements. And then when they are recognized, you're able to perform checks according to multiple standards shown in the middle of the circle. And when you receive your outcomes, you're able to report them automatically. And if something is not passing the rules of the standards, you're always able to optimize by change of the shape of your member or weld size, thickness of your plate field for plate buckling, and so on. And the main idea here is that you see these arrows, they made on purpose. The idea is that if any changes are required in your model, all this process is repeated automatically. Basically, what you need to do is to update your model, synchronize with our software, and regenerate report. And all these intermediate steps will be repeated automatically. Okay, I will briefly walk through all these items. Basically, since we are now today we're going to talk about the post-processing. One of the most important things we will talk about is of course, load combinations. So on this slide, you can see the example from one of the industry standards. How do you need to deal with the load combinations? Basically, they change a little bit depending on your industry, depending on what actions do you need to account for, but the main idea is the same. So if you have the separate loads, you need to combine them in a way to create the worst load situation, which potentially can cause problem in your structure. So you need to make sure that the received results are well within the allowable limits. How does this table work in SDC Verifier? On the top right corner, you see the standard window of the software. And basically, this is kind of matrix functionality. It can be linked together with an Excel file. We know that a lot of engineers get used to use Excel files. They do some kind of templates for the load combinations. So the idea is that you're able to simply prepare the load combinations in your Excel file you get used to. You can copy and paste directly in the SDC Verifier window. If you don't want to do that, you of course are able to do that directly in the software, like it's shown on the screen. So what does this load combination mean in general? The idea is that in SDC Verifier, we have three main items. This is individual load, load set, and load group. And the idea is that individual loads represents a single output set from your load. Yeah, so if you use FEMAP, this is one output set. If you use ANSYS software, this is basically one step, result in one step, and so on. And the idea is that you do the linear combination of separate loads to get the results of your load combination. And if you want to find out in the end the absolute maximum results over the different separate loads, load combinations, etc., we came up with a separate item we call load group. This is kind of envelope of set of results which shows absolute maximum over the load combinations included in this load group. It is very useful to use it, especially if you have the different type of your load situations. For example, if you have the regular load situation, which does not take into account the wind influence or any other things like this, and if you have the wind load separately, and also maybe some exceptional cases which might appear rarely, but that's still prescribed by the standard and you need to account them for. So it is nice to present your results over different load situations and see, okay, what is the real cause of my problem and how important is that in real life. And so this is again the same example in the standard, but a little bit more extensive one, and it's not the more extensive ones are not no exception, because you can use several loads and you can use hundreds or even thousands. So it is unlimited, and it is up to user how many different load combinations do you need to include in your software. Since I just mentioned about the recognition item, so basically we can recognize them all, execute checks according to different standards, check the stresses, displacements, results of fatigue influence, weld strength check, or even a result on bolts. You do that according to a lot of standards. But then we have a question, okay, if I have any problem in my structure, how many times do I need to repeat it to get it okay in the end? And on this screen, you can see the traditional workflow of the verification programs different to compared to SDC Verifier. So basically, if you calculated your original design, it's turned out to be okay. This part of my structure is overstressed. I need to reinforce it. Basically, what you do here, you calculate your original design. You do the export to your separate FEA software. You check it. You find out in the end that it's not passing the rules. You do changes in your model, you repeat it, you need to again export that, and basically you are running in circle. And it can lead to a huge number of different iterations to get it completed in the end. What our software does, basically we keep everything within one model, and all these intermediate steps they're skipped automatically. Because if it's turned out to be that a certain part of your structure is not okay, you do update within the same finite element model and you directly run the same report or check on top of this. Yeah, so it is a huge time saver, especially if you want to get it improved or to get it reinforced, whatever. But the today's webinar is gonna be, okay, how do I need to improve and how can I quickly do that? How to understand that this thing help and another one does not help. So on this tool, basically you see two main cores for this, which helps to reach this goal. We call that peak finder tool and the governing load tool. The difference is quite simple. So the peak finder tool, it helps to never miss your hotspot in a model. Very often engineers use complex structures and a lot of sections they model in detail, and you have a lot of areas which can be easily overlooked. So basically, if you're interested in a certain level of stress and you want to quickly find out, okay, how many spots do I have with the stress level higher than this level or another one? This tool helps to automatically recognize the zones of your structure based on certain criteria. So if I want to get, let's say, 10% of my structure overstressed, I quickly get it, and I can generate it with the plot or with a table like shown on this screen. Or if I want to find out, okay, show me all areas with the utilization ratio higher than 1. Yeah, so it shows you directly. So you do not spend time of thinking, walking through all these locations, etc. But then we have another problem. Okay, I've got my overstressed zone, but why it happens? What load causes this problem and what load situations? Because you're lucky if you have, I don't know, 2 loads and 5 different load situations, but very often you have much more. Yeah, so dozens or hundreds or thousands different load situations. And it is not only quite complicated to find out where it came from, but it also time consuming to analyze all them. And if you do the reinforcement on top of your structure, you need to walk through all of them once again, because if one load combination causes the problem in one spot of your structure, it does not necessarily mean that another one is negligible, because this another one load combination can cause the problem in the different part of your structure. So what can we see on this plot? We can see basically the distribution of the different load combinations over the certain criteria. In our case, this is a stress level. Yeah, so the idea was that initially we had 132 different load combinations, but when we analyzed all them, it turned out to be that 8 load combinations cause the highest stress level, and the rest 124 load combinations are basically leading to the lower stress level. What does it mean in terms of time execution and engineering solution? It means that all these load combinations except these 8 can be simply ignored, because they do not lead to the higher outcomes than we're interested in. So it means that basically we can analyze only these 8 load combinations for also design improvements if we do some local improvements, and another one can be skipped. So this is a huge time saver, yeah, because instead of this 132, you could have, I don't know, 1,000 of different loads. And what's more important, if you want to find out, okay, what specific load situation, what is position of my structure, which is the governing one, it can be received in a second and highlighted with the plot. But then I think, okay, I've got my 8 different load situations, but one load situation includes 10 different loads. Which loads do I need to focus on, and how to improve my design? For this reason, we improved it deeper, and basically we came up with a little bit more extensive approach, which shows the influence of the separate individual loads on the magnitude of your outcome. What you can see on this plot is basically the same 8 different load sets. Each of these load set is causing the high stress level, which is highlighted with this long column. Yeah, so with this graph. But then, besides this distribution, you have the very detailed distribution of the individual loads. Yeah, so how to read that? So I see that out of 1, 2, 3, 4, 5, 6, 7, so 8 different individual loads included in one load combination, only 2 individual loads are causing the really high stress level, while the rest of your loads are relatively minor. So it also gives you an indication where do you need to look at. Yeah, for example, if I'm focusing on the stress level, it's already kind of indication that these 2 loads are the governing one, and if I do any changes with them, that is crucial. for stress level at this zone. And of course, for more details, you can get the complete table extracted where you can see that, okay, percentage influence in this load set is 38% from platform load and 27% from conveyor load. This is basically how it works. Yeah, but this is all theory. In this webinar, we're going to directly dive into a specific model and see how it works on example. So for this reason, I prepared a simple model. This is basically a lattice structure, but it contains quite a lot of different members. And yeah, it can be whatever model you build up. It can be solid elements, plate elements, beam elements, whatever it is. But the core of the problem identification is basically the same. So what do we do here? We have a lattice structure and we have 11 different loads applied separately to the structure. So this is the on weight from the equipment, platform dead load, handrails. We have the another platform load. We have conveyor load, and we have wind load in different directions, which is acting on the structure. The only thing that this is transferred with forces. So what do we do here? This is the main window of SDC Verifier project. Basically, that's how it looks like. And we're going to the main tree, to our jobs chapter, because this is where all these loads related things are stored. So as explained before, we're going to focus, we're going to create 11 individual loads. Basically, each individual load, this is a FEM load in a model in combination with the boundary conditions with your constraint, which is applied at the ends of the columns and also at the ends of these conveyor supports. Yeah, so we analyzed all these 11 individual loads. Basically, the analysis runs pretty fast, so I'm lucky today. But what do we do next? We're going to focus on the specific load situations, because these 11 individual loads should be combined together to determine the worst load situations prescribed by the standard. I will edit simply this in a way I do now, but the idea is that although I have it already predefined, the idea is that you can prepare it in your Excel file, you can copy and paste it directly in this window, or you can do it in the way it looks now. So you simply can type the amount of load sets you need. Basically, you fill in the factors you want to apply to your loads. Yeah, so if I type the factor here, let's focus on this particular load situation. It means that my individual gravity load, so my own weight of the structure, is going to be 35% increased, while the same is also repeated for the other own weights. And the platform load is increased 50% in this case, as well as the conveyor load applied at different spots, while the wind load is 10% reduced. So this is how do you need to treat that. And all these actions, they occur simultaneously. Right, so besides that, I'm using also a safety factor of 1.15. So these load combinations, they are quite comparable to the Eurocode load situations, but you can also do your customized requirements, let's say prescribed by the company, or specific requirements for your real load situation. What I do here, I combine them all together, having the different directions of wind influence. So you can see the signs applied to the wind load in different directions. And then I repeat the same thing also for regular case, when I do not have any wind load at all, because I want to know, okay, what happens if I do not have any wind? What happens if it happens with wind? And I would like to find out what happens in this kind of exceptional case when my conveyor load and the platform load are significantly increased. So I applied the partial safety factor of 2.5, means that my net value of conveyor load is going to be 2.5 times higher compared to what is in the model. as well as the platform load, which is 50% higher. Yeah, so this is a brief description on the load combination. And then when I already created them, I've got 23 load sets from 11 different individual loads. But again, important remark, you can extend it as much as required from your side. Doesn't matter whether it's one load combination or 1 million of them. Yeah, so it is up to user. But we now deal with this simple example. What's next? We have the load groups. So basically, I decided to sort all these load combinations by the different influence. So I have the regular case with no wind, which contains these specific load situations. Wind case, basically my wind influence. An exceptional case, which is these two extremely high conveyor loads. And everything else basically can be removed. That was done preliminary. I didn't do that. For now, we do not need that. And then the only thing you need to do is to basically run your calculation. But I already did that just to do not waste our time. And I've got already the outcomes. So what I'm going to do now, I'm going to check, okay, what is the stress level based on the envelope of load of these load situations. So basically, maximum stress level over the all load combinations. I'm going to make a simple plot. I make a right click, I go to contour plot, and then I select stress. Okay, I'm going to preview this plot. And then what I didn't remove the connector elements, these red elements, which are basically required only to transfer the loads. So this is what I'm going to do now, because we want to get a nicer picture. And then we repeat the same thing. Yeah, this is better. Okay, what we see on this picture, we see the overall stress level, basically the maximum stress level, and we focus on the 235 megapascals as the limit, because this is the yield limit of our structure, and we're gonna compare the calculated stress level to yield limit. But different standards, they prescribe the different requirements, so you need to account for the safety factors, various ones, and so on. But I already see that a lot of my areas, which are highlighted in red, they are having already a stress level which is higher than the yield limit. Basically, this is something we would like to avoid, or at least explain why that happens. Okay, so this is basically clear. But besides the stress level, since our model is made of the beam elements, and a lot of columns and beams are the standard components of this lattice structure, I decided to perform the member check according to Eurocode 3 standard. So what is the idea of this member check? The idea is that you compare the resistance of your cross-section and the member according to Eurocode compared to the forces which appear under these loads. Yeah, so your actual forces, bending moments, shear loads, all these kind of things are going to be compared with the actual resistance, bending resistance, and also buckling check done on top. And what is more important for buckling here is that buckling length, buckling check is highly dependent on the buckling length. So what does it mean? First of all, a few things. How does software does this check? If we have the BIM model, basically we're able to recognize all joints. This is the intersections of the structural members, and these joints are used Sorry, somebody's speaking on the background, but is there any question? Or
I think it was non-intentionally. I mute the person.
okay.
If she want to say something, just unmute.
Okay, doesn't matter. By the way, if you have any questions during my presentation, do not hesitate to unmute yourself and directly ask. Maybe that will shed a bit of light on the specific problem. Okay, coming back to this, how do we recognize our members? We use joins, the intersection between our members, and we determine the beam member length. And the feature of this, especially for buckling, which I mentioned, is that the beam member length can be different in different directions. On this example, you can see that the length in Z and Y direction, so basically in our major and minor directions, are different. Yeah, because this length, the stiffness is different. So if I have it in global Y direction, so perpendicular to my member, it is split into two different sub-members, and your buckling length is twice as less. Well, in major direction, it is bigger, yeah, because the stiffness in this direction is determined by those two 3D joints. So it is extremely important for the buckling check, and these things can be done automatically with the help of SDC Verifier. So if I go to the beam member finder, basically what I need to do is to simply find all the members. I can remove them all, and I can in 1 second recognize 349 beam members. After that, I can also plot them. What I see here, that out of my finite elements, I see the clear determination of the beam members. You see, so basically from joint to joint, all the members are correctly recognized. I made a plot in Y direction, but you can of course repeat it in Z direction and then do checks in both directions for buckling verification. Yeah, but this is a small introduction. What are we going to do besides the axial and bending resistance comparison? Okay, we're going to go to the member check according to Eurocode. Basically, this is the main window. I already have the pre-created standard. And what we're actually interested in for now is the last check. This is buckling and overall check. And this check shows you the overall maximum utilization ratio over all these checks. So shear check, axial, bending, and axial, buckling, compression, torsional, lateral torsional, and cross-section overall checks are already included. So we're going to focus only on highest values of these things. I'm going to create component extreme table over selections, and I'm going to select all beam members from my model. Yep. So I have a quite long list of them, and I'm going to focus on first overall load group, which contains everything. So what it shows me the results of all these kind of checks with the maximum value in the end. This is utilization factor overall, but then for each of these members. Yeah, for a lot of them, you see that the calculated ratio is within the allowable limits prescribed by Eurocode, but some of them are highlighted in red. And that is something we would like to pay attention on, because it means that the resistance of this member is not enough compared to the rules of Eurocode standard. And so I will scroll down quickly just to highlight that there is quite a list of members which are overstressed. And then in this case, we would like to see, okay, but which are actually overstressed? I'm going to go to the peak finder tool, but before I do that, I was presenting to you a stress level on the structure, and I made a simple static stress check. So I compare my calculated stress level to the yield criteria of my model and 70% of tensile stress level. Basically, this check is also available and can be quickly created by you. If you go to the Add Custom Check, you create this, then you click execute the right click, go to the predefined, and there are simple checks like the one I'm going to use now, static stress check. Yeah, so this is a rough comparison between the calculated stress level and the yield and ultimate criteria. So just to highlight the story, we were focusing on the stress level, and now we're focusing on the utilization factor. And with this plot, you can already see, okay, some of my spots are similarly highlighted in red, but then I directly see that orange and red elements are not passing the rules of this simple check. Okay, let's figure out what is the cause of this problem for beam member check and also for stress level check. I'm going back to my SDC Verifier project, click Save, and I go to the peak finder and the governing load tool. I'm going to delete the existing one that was just, I was playing with things. I'm going to remove them all. Doesn't matter. Yeah, and we do everything from the beginning. So I'm going to create a peak finder table based on the static stress check criteria, but you can directly see that we can also focus on the beam member check and the static stress check. So it is up to user whether you want to focus on the verification criteria according to standard or on the load criteria. So basically you can focus on the stress, principal stress, your internal forces, weld stress, and whatever you're interested in. This is up to user. For now, we're gonna focus on the static stress check, and then we will go deeper. So I'm going to focus on the overall utilization factor value over the all directions. And I basically interested only in all the values which are higher than 1, because it will mean that our stress level will be higher than the criteria we prescribe for this check. After this is created, we can go to the tables, execute the right click, add table, and see that, okay, we have all entities automatically included. I'm going to replace them with the selection we are now focusing on. I want to get rid of all these connectors, which are not actually the, or maybe we can make it even easier. We can go to the beam members we were focusing before. I will select them all. And what I basically need to do in this table is to make sure that I use the right load for this. For now, we are focusing on the envelope load, which contains everything. We set up selection, and here at the bottom, we have several options. First of all, I would like to pay your attention on this option, show only welds. That will mean that if you have your welds recognized in a structure or joints, whatever you use, you can show results only for those areas. Yeah, but if you don't want, if you want to see that for the entire structure, you can switch that off. And basically here is the list of things you would like to highlight. So first of all, this is the colors, the plot type you want to see in the end. So you want to see that highlighted with the element values for zones, maybe on a specific selection and so on, but I will stop on this in details. Let's view the table and see which zones are actually overstressed. Yeah, I have quite a lot of them overstressed here. You can see we have now the full list of things with the higher value than 1. but it is presented with the zone. So we see that zone 1, and then we see that it contains 5 elements. Zone 2, it contains 3 elements, and so on. I think it worth to explain what does it mean, basically. What does this zone mean? Each zone is recognized automatically. So basically, your zone indicates the number of finite elements linked together which are overstressed. So as long as these elements are linked together and overstressed, this is indicated as one single zone. And then if you have another area which is separately overstressed, this is another zone. Yeah, so you could have 5 different elements, and they are all linked together, and they create zone 1. The same as 3 elements create zone 2, and so on and so on. Yeah, and this value is shown as the maximum value per each of these zones. So it means that some elements out of these 5 elements are having the value of 2.59. Yeah, and you can directly see the governing load for this value. So load set 26 is causing this high value. I'm going to plot these things to get a better idea. What does it mean? Sorry, I noticed that I selected simply value. We'll let it be anyway. Okay, so on this picture, you see all the zones highlighted with the higher criteria than we prescribed. And we see that on top of this zone, we see the highest magnitude. What we can also do, we can indicate that with numbers. So we can see ID of each zone, which is shown in this table, and we can also see the value, which causes this stress level. Yeah, this is much better. So basically, what we've got one complete picture which highlights separately all zones with the utilization factor higher than 1. But this is some criteria which we prescribed at the beginning, and this is easy adjustable, because somebody of you might say, okay, but I don't care about this utilization factor, what is higher than 1. I want to get everything which is higher than 0.5 and less than 0.8. Yeah, it is also possible, because you can set up the range of these values. And then if you go to your table, you click fill, you see, full list of these elements is already received, and you can make a quick plot for the double check that it corresponds to each other. Yeah, so these values are within the range from 0.5 till 0.8. Quite a lot of them, because this is basically something which results in the low stress level, but anyway, this is received. Somebody of you might ask, okay, but I would like to get basically only 20 elements with the highest stress value, and you can do that. So if you don't care about all these thousands of small peaks, and you would like to focus on the really high stress level from 20 elements, that's no problem. You see the list with 20 elements which are having only the highest value of your stress. And this is also possible to show, okay, how much, what is the percentage? Sorry, I was clicking a few times. You might ask, okay, how many elements are overstressed from the 1% of the total number of elements in our model? And we can do that. Basically, you set up this 1%, you fill your table, and you see the full list. Yeah, so this is up to user up to all results you're interested in. And of course, this is repeatable for another checks and also for stress level, because if you don't care about these utilization factors and you would like to see, okay, I want to see only stress level higher than 235 megapascals. And this is all fine. We fill it in, and we've got the full list of the same members. Basically, they correspond to each other because utilization factor is comparable. But then there is a question. Okay, I have this list of zones, but I still do not get what is the cause. I see that, okay, it's coming from load set 26, this one from load set 7, but how to improve my structure? What you can do actually is you can select all these zones, and you can directly go to the governing load tool. And the idea is that each of these zones will be automatically stored in the selection of your governing load tool. Yeah, so, and you have the same option here. So whether you want to focus on stress level or check, whatever it is, since we started from stress, we're going to continue with this. And you set it up. We make sure that we still have the same load. Yeah, so this is envelope of load sets. We focus on the stress range higher than 235 megapascals, and we fill the table. I've got basically you would say this is basically the same table. What's the difference then? But the advantage here is that you can focus specifically on each of these zones separately. So if I select first zone, which consists of 5 elements, I have the list of things on the right. Basically, what I can do here, I can export all these governing load situations which lead to the highest stress level per each zone in the load group. Yeah, so I see that I have load set 26 is causing the highest stress level at first 3 zones. Load set 7 in another one, load set 26 in this 3 or 4, and so on. But I would like to store them all in a separate load group and keep as the governing one, because basically these load combinations are the governing in terms of the stress level. And this is what I'm gonna do. So if you click on this icon, there is an option you can export selected items or all the items, but since I selected all, doesn't matter. I do export and I write governing loads stress level. I click OK. I click OK just to close the governing load table with the Pick Finder tool. And I'm going to go to our job to show you that the separate load group, which consists all these governing loads, is automatically created. You see? So basically, you've got how many? 2, 3, 4, 5, 6, 7, 8, 9 load combinations, which are really important in terms of stress level, out of 23 different load combinations. What it also means is that if you're focusing on the stress level, and I don't know, you might change the plate thickness of your eye shape or thickness of your tubular shape and rerun all calculation, but rerunning that for all 23 load combinations, that might be a little bit time confusion for somebody of you consuming. So you can only rerun basically these 10 which are important and which are causing the highest stress level. So that is the big time saver in the separate cases. But we're going to go back to our governing load table. We fill it in again, and we want to dive into more details. All right, I have my 5 elements, basically, which are caused by the load set 26. What I want to do, I want to, first of all, make a plot. Where do I have them? Let's plot all with the value label. So this is not entire structure, but these are separate overstress zone. And you can quickly find out their location in the model. This picture is not the best. Basically, you see only overstressed areas. We can use also the entire structure, and they will be highlighted in a way as it's shown for the peak finder. But we're going back, and we see that 5 elements. The highest stress level is caused by load set 26. If we click on this icon, we're able to see the separate detailed influence of the loads included in these load combinations. So you see that the highest stress level is coming from the load set, but basically those 2 loads are a conveyor load. So if I drag my mouse in here, it is also highlighted on the graph. So it is easily to navigate yourself through all these values. So we see that the governing loads, only forces, and the platform loads are the governing ones. Yeah, this graph is very nice to quickly understand, okay, which ones are important and which are not. But if you want to get more details, you can also click on the same icon and go to the load set contain peak element table. If you click on it, you get all these details stored in a table. So what I see here, I see that my platform load and conveyor indeed result in the relatively higher stress. So it is 30 and 50 megapascals. And basically, what is big advantage here is that if I want to improve my design, I can only focus on those 2 loads, and the rest of these loads included in the load situations are relatively minor. Yeah, especially if you want to find out the behavior of your structure, the moment which acts, and so on. These loads are a very nice indication criteria. What is more important here is that all these can be repeated for every overstress zone, and you can store them also in the reporting. So if I go to my report, I will create a new one. If I go to the post-processing chapter, governing loads, and also peak table, I can import that what I already created. Okay, but I would like to make a custom structure, since I don't care about all the things. So I import what I created in the peak finder, in the governing load, and I show that for all the details, I can plot all zones on top of the picture, load set content. I can create table with info. I can include a detailed plot for each of the zone, summary plot, and so on. And so then you generate your table. That might take probably a few minutes, because I have quite a list of zones. This is more than 380 items. But some of them are basically already generated, so we can interrupt the process and see what is already generated, just to see as an example, and do not wait it until it stops. If I click stop, and so depending on how many overstressed zones you have, yeah, that could take time to generate all them in the report. But the idea is that you have every zone with the value of your result. You have the governing load, you have all them highlighted on the picture, and what's more important, each zone is presented separately. Yeah, so you see the table, you see, okay, what is the value in my zone, where it's coming from, then it is repeated for every for every zone and gives you an indication where it's coming from. But then you go to the governing load tool, and you can also repeat the same thing for every zone with all these graph and tables. And sort it over the different overstress connections. Okay. Yeah, so all connections with the detailed influence from each individual load are described, and this table, which I basically presented to you, is also shown here. So you see that the biggest stress is caused by the load combination, and then you see, okay, the full list of individual loads included.
Roma, we are running out of time. Maybe we could go to Q&A session.
Yeah, just give me 2 seconds, and we start Q&A. So this table, you see the factors in the load combination, you see the net stress value in the load, and then increased stress due to these factors and the percentage influence in your table. That gives you a precise understanding why it happens, what do I need to do to improve it, and maybe I need to improve my loads, because it can be that you might assume conservatively a certain value of your load, and you can reduce them till the more realistic magnitude. So that is the whole idea. You start from the load set, you swap to the separate influence, you focus on each zone one by one, you quickly generate it in a report, and you improve your design. Well, I hope I didn't hear any interruption during the process, so I hope that everything was clear. And we have 2 minutes until the end of the webinar, so we can go to a Q&A session, which Petro mentioned about, and I'm ready to answer the questions.
We have a question in the chat from Spyros. It's where does the safety factor value of 1.15 apply? Is it a material factor?
This 1.15, in our case, it is applied as a safety factor. Yeah, so if I see this column, this is 1.15. And basically, this factor is applied to determine allowable stress in our custom static stress check. Yeah, so our yield limit divided by 1.15, this is our allowable stress value, and that is where it's accounted for.
Also, I have one more questions. It's can the governing load tool be applied to bolt checks or any other checks?
Sure. So if you do verification on the bolt check, basically what is crucial for bolts is your forces transfer through the bolts. So if you compare your shear load transferred into the bolt, and that is causing the high utilization factor ratio, what you can do, you can pick up your bolt into selection in the governing load tool, and you can, instead of focusing on the stresses, you can focus on alignment force, select, let's say, shear plane force, and find out which load causes the highest shear load, and basically this is your indication. The same thing is applicable to the weld strength check, because you do the force summation, and you can also focus even on whatever it is, member check. All of these things are can be used as the parameters you're gonna focus on.
Yeah, maybe someone else want to ask. Just unmute yourself and ask one more question, maybe.
I have a question. Has this session been recorded? Sorry, I haven't been from the very beginning, and will it be available?
Yes, it's recorded, and we will send you a link to YouTube video maybe tomorrow or this Friday.
Perfect, thank you. Yeah, it would be good to click through it
Yes,
by myself. So thank you.
The main message is here that governing load tool does not solve the project for you. I mean, it does not solve your engineering problem, but it significantly helps you to solve it. Because if you see that something happened, something went wrong, I have inordinately high results in my element, okay, it shows you where it came from, and you do engineering decision. Because if I see that my member fails due to bending check, you can find out, okay, what is the governing load for causing this bending moment in my member? And you can reinforce that in that direction. Yeah, so this is a nice tool focusing on the governing parameters of your checks. Well, I hope that this brief demonstration was pretty clear and informative. Otherwise, you can also ask your question. You can write an email using the mailbox here. You can write to our support, call directly and request trial for SDC Verifier if you didn't do it yet. Thanks for attention, and yeah, see you see you the next time.
Thanks. Bye.
Thank you. Very interesting. Bye bye.
Thank you.